and just ignore the fact that that's there, perhaps. So, you know, one of the real, and we saw this, I did a little preview problem the other day, that was a calculus problem, a preview problem on Monday, and one of the things in there was a big trig function, but it was, but we worked on a tangent line. And anyway, my point is that lines are real important, and if I open the book to section 1.2, they talk about lines. Anyway, lines should be, I mean, I'm trying to review some algebra and trig. You should be good at lines and slopes by now, but can you can you graph a line like this? I mean, I don't know how you would. How would you do it? Talk to me a little bit here. I guess I'm asking you to graph it. What would you do?
I get y by itself.
Okay, so he's saying, and he's not the only one. He's thinking about this. He's thinking about this formula for a line: y equals mx plus b. And that's a good formula for a line. That's called, I don't really care what it's called, but it is called slope-intercept form. When you're in this form, you see the slope and the y-intercept. This is a good form for a line to be in. So that means you have to solve for y, right? Do a little algebra, solve for y. You should be able to handle that. You know, I'm just going to skip that a second. I'm going to do it a little differently. Monday, when we did start, the only little bit of math we got into was x and y intercepts just a little bit. Let me just start with that. If I wanted to find the x-intercept, what do I do if I want to find an x-intercept? Plug a 0 in for y. Now watch how I do that. In this format, I go like this. I just plugged a 0 in for y. And it's zeroed out, and I solve for x, and what do I get? Plug a 0 in for y. I'm doing it in my head. I guess I'm doing it in my head, if you don't mind. 18 fifths? Okay, 3.6. Okay, thank you. You guys are awesome. There you go. 18 fifths, so that's the x-intercept. So that's 1 point on the line. I want the y-intercept. How do I get a y-intercept? Plug 0 in for x. This is always true. I'm going to plug a 0 in for x. Don't lose that negative sign there. Divide by -3. I guess the y-intercept is -6. Okay. Which is, if I try to stay in proportion here, that's way down here. -6. Try to. And anyway, with those 2 points plotted, you can draw a line, right? A line only needs a couple points. I mean, it's a line. There it is. So there's a picture of it, kind of one way, using plotting a couple points. Not just plotting any points, but an x and a y-intercept, which might be important. I think your first little review question on your review sheet is a lot like this. I think I asked you for the x and y-intercept, and you could work like this. You can work other ways. You know, you can work however you want. I'm just showing you some things. Sometimes I show you a lot of ways. Students don't like a lot of options. Sometimes students want one way to do things. Well, I'm sorry. There's a lot of ways to do algebra sometimes. As long as you don't make mistakes. So anyway, I graphed the line. You know, if I also might want to know his slope, maybe you could just tell me his slope. You know, this is where I might use his advice. You know, if I want his slope, it would be nice if it was in this form. When it's in this form, the slope is staring right at me, right, you guys? It's that number m in front of the x. It's not that number in front of that x, but when it's in that form, it's that number in front of x. Okay. So I could do that, or if I understand what slope is, you know what slope is. It's rise over run. It's the change in y over the change in x, which implies, you know, you got a couple of y's, you subtract them. You got a couple of x's, you subtract them. This is if you have a couple of points, you subtract the y's, you subtract the x's. You try to see the slope is the ratio of the rise over the run, or the change in one variable over the change in the other variable. It's a ratio. Sometimes we use the word rate of change. I mean, how many ways can I talk about slope? It is important in this class. I mean, in calculus, slope is one of the big ideas, and you sort of saw it Monday. It's, well, I don't want to, it's hard to, I got to stop from previewing too much. Let's just stay where we're at here in a minute. But anyway, so I kind of see it here. Look at this. If I just look at this, I see myself rising and running. If I use the 2 points I plotted, I rose 6 and ran 3.6. I could just say my slope is I rose 6 and that's my rise and that's my run. I could say that. That's my slope. Can you pick up a calculator and tell me what that is? 1.66666 repeating. Damn. Okay, that's okay. Listen, when we're doing math, and this is, maybe we should get this out of the way now. Sometimes I argue with students about getting the exact answer or some kind of rounded off answer. It sort of depends on the setting and what we're doing, but it seems like when we're doing math problems, I kind of want it to be exact. So I don't want to round this off and call it 1.7 or 1.67, or I kind of want it to be exactly what it says, and that means I got to write 6 forever. Is that what I got to do?
You got to write 4 of them.
4 of them. Well, there's more than that.
Put a line.
Yeah, you put a little line over it. There you go. Now, that's exact. That means it goes forever, right? That's technically, that's what that means. And without that, you've rounded. Without that, you've rounded it off. I mean, if you write 4 6s and stop, you've rounded it off, and it's not exact.
I forgot that my calculator rounds itself.
Yeah, it rounds, right. So when you see 1,000,000 6s, you might think, oh, it only has 9 or 10 6s. No, it's got an infinite amount of 6s. Your calculator only has 9 or 10 spaces there. What's my point? My point is I want exactness and not rounded off decimals, I guess. But now wait a minute. If we move to a word problem or different settings, different problems, rounded off decimals are totally appropriate. But once they're rounded off, they're called approximate, and they're no longer exact. I guess, here, so now I'm off on a little side subject about exact and approximate. Let's get this out of the way, although I think we'll argue about it all semester. And I don't mean argue. When I say argue, I just mean discuss. That's what I mean. I don't argue with my wife. We discuss things. Hey, do me a favor. Solve this equation. Solve this equation, please. What would you do?
Add 2.
Add 2. Thank you very much. You would add 2 to the other side. Then you would take the square root of both sides. This is doing algebra. And you would get an answer, x equals...
Plus or minus.
Ooh, good. You should introduce the plus and minus symbol. That's true. You should introduce the plus and minus symbol when you square root both sides, because there are 2 answers. You're right. So it is plus and minus the square root of 2. And that's how we write that number. If you chose to decimalize that number, you will be writing forever. If you don't write forever, that means you'll round it off someplace. You know, the square root of 2 is an irrational number. Its decimal will not repeat a pattern. There won't be a pattern, and if there's no pattern, then there's no way to put a line over it. And so the only way to represent the square root of 2 exactly is to use this symbol. Now, roughly, what is it? It's 1.414. That's good enough for me, but that is rounded off. It's a decimal that goes forever with no repeated pattern. That's what an irrational number is. To represent it exactly, we use this symbol. To represent it approximately, we use this. And maybe we agree on how many decimal places we want. You with me? Those words, exact and approximate. That's an approximately equal to symbol. Squiggly equal sign. guess it should be plus or minus. Okay. All right. I can spend hours on that subject. No, that's good enough, I think. So this answer was a funny repeated decimal. That's what brought that whole thing up. It's a 1.6 forever. The best way to represent that exactly might be with a fraction.
Right.
It is 1 2/3. Maybe you knew that. 1 2/3 written as a fraction is 5/3. I mean, that's my slope.
Isn't it supposed to be negative?
Was this slope negative? Was it negative? Let me see. Look, I kind of just went on the picture and I went up 6, which is positive, and to the right 3.6, which is positive. No, it's a positive slope. And by the way, when I look at the picture, lines that slant that way have a positive slope. When it's a decreasing line like this, that has a negative slope. What about this line? What's the slope of this line?
0.
Yeah, it's a horizontal line is the word. And what's the slope?
0.
0. Right. So here's a negative slope, a positive slope, a slope of 0. There's this other one that's kind of funny. It's a vertical line. Has an undefined slope. Do you know why? How much does it rise? A bunch, yeah, infinite amount, or you could say it rises 2, or you could say it rises 10. But how much does it run? 0. So as soon as you write 10 over 0, that's undefined. It's got an undefined slope. Right. So cool. We're talking about lines. We're talking about slopes. We're reviewing as fast as we can. Still on the subject of lines, one of a step up kind of would be is always this question when we say find the equation of the line. So this is backwards, what I like to call a backwards question. Find the equation of the line, and I'll just say that goes through, and this is pretty basic algebra in a way, but it's worth going over, I think. That goes through the points 5, -13, and 4. I'm sorry, -4, 7. So again, backwards, just to kind of set this up again, if this problem said, I gave you the equation of the line, and I asked for some stuff. Can you give me a graph? Can you give me some information about the line? X-intercept, Y-intercept, slope. You with me? But I gave you the equation and asked you some questions. Now, I'm giving you some information, and I'm asking for the equation. And by the way, I don't even want a graph, I guess. I don't care about a graph here. But I do want the equation. And so to get the equation, that's kind of what I call a backwards question, and that takes a little more work. I like this formula. You guys might have different thoughts because you can do algebra a little differently. But I like this formula. When someone says, find the equation of a line, I tend to go for this formula. This is called point-slope formula. And you can get yourself the equation of any line if you know the slope and you have a point. If you have a point and you know the slope, you plug the slope in there, you plug the point in there. You leave the variables x and y. You need some variables in your equation. And you can get the equation of a line. So if I am going to use this to get the equation of a line, I need the slope. How do I get the slope?
y2 squared minus y1.
Thank you. If you have 2 points, you can get the slope. You need 2 points to get the slope. Yeah. All right, let's do it. There's a little 2-step problem then. First step, let's get the slope. The slope is the change in y, the 7 minus the -13 over the change in x. -4 minus 5. You could subtract them in either order, but be consistent, please. I subtracted this y minus this y, so I did this x minus this x, and this slope is 20 over negative 9. Or, you know, when the negative sign shows up in the denominator, I like to just move it to the numerator. It's the same value. That's my slope. Again, this is a place where I don't want to decimalize this. If I decimalize this, it'll be a rounded off decimal. Well, I don't know, I'm picky about that. I like exactness. The way you keep this exact is you leave it as a fraction. It's exact. Right? If you made him a decimal, what do you know what he would be? I know what he'd be. 2.2222222222222. Repeating. Negative 2.222222222. Right. But anyway, negative 29ths. Okay, what now? Oh, I got the slope. And if I pick that, use that slope, and I use one of these points, I don't need both of them, I can write the equation of a line. Y minus that y value 7 equals this negative 20 over 9 times x minus that x value negative 4. There you go. There's the equation of the line. We usually don't want you to leave it like that. You're just kind of got started there. Distribute, clean it up a little, and maybe to leave it in this form would be nice. I'll just do that with you. This is all review. I'm sorry if you're bored, but not that sorry. Lines are important in calculus. We should be good. We should be good with lines. You made it to calculus. You should be good with lines. What did I do? I called that a +4. I think I'll distribute this here. Negative 20/9 times x. That'll be negative 80/9. I'm going to add the 7, you guys. That means I need a common denominator. I love this. Yeah, it is 7 over 1. That's 63 over 9. I'm going to add it to that. I think my answer is negative 20/9 in front of the x. And then when I add those with a common denominator, negative 17/9. Wow. Cool. Maybe you can get a calculator to help you with this, but again, I'm trying to use my fractions to avoid rounded off decimals. That's what I'm doing. Cool. Yeah, that'll be important. That might show up on your little review sheet. That might be enough about lines for the moment. Any questions on this as we're talking? You can interrupt me and get my attention and ask questions anytime. I may be in the middle of a thought and I may just put you on hold a minute, but you can always interrupt me and try to ask questions. Just for fun, if I did want to graph that line, nobody said to, but just for fun, graphing the line, I graphed this line and I did it a little differently maybe than most of you wanted me to, but graphing that line with this formula, which it's in, is pretty easy. You start with the one point you know, which is the y-intercept. What's the y-intercept? Negative 17/9, which is, of course, right here. Everybody knows that. It's almost -2, I guess. Anyway, negative 17/9. And then what am I going to do? I'm going to do my slope. I'm going to count my slope. I'm going to go down 20 and over 9. My slope is down 20. Jesus. 20 and over 9. Hang on a second. What is that? What did we say that was? Negative 2.22222 repeating?
Yes.
Well, let me just try, instead of going down 20 and over 9, can I go down negative 2.222 and over 1?
Yeah.
It's the same ratio. It's the same slope, right? So down roughly 2.2 and over 1. Okay, I'm roughly doing a pretty good job here. That's my line. If I would have went down 20 and over 9, it should have landed on this. It should be fine. Again, it had a negative slope, so it looks a little different than that line. That line had a positive slope. This line had a negative slope. That's a big concept about slopes. It's fairly easy. The line's decreasing or the line's increasing. By the way, sometimes the word decreasing and increasing can be confusing. It's not confusing if we all agree to read left to right. But if somebody is trying to read right to left, it's really confusing. Are you with me? So, if we agree to read left to right, that line is increasing. If we agree to read left to right, these y values are decreasing. The line is decreasing. But if somebody was reading that oppositely, let's not do that. Cool. You know, I think I'm going to kind of flip to the next section in this chapter 1, which says functions and their graphs. I just want to, I don't know how much I want to do here, but I thought about this, and maybe I should actually do a homework problem that I've assigned. I mean, we're in a little tough spot, trying to review all of algebra and trig, but I think we're doing okay. I'm hitting the high points, and that is lines. But once I move past lines, there's all kinds of functions. But in a way, I want you to know that there's not that many. Listen, you know, and when I write a function f of x, you all know that that is just y. It's just another name for the variable y. The input variable is x. F of x is the output variable y. But, you know, if I write that, that's a line with a slope of 1 and a y-intercept of 2, and right? But once I start throwing some exponents on it, then you get an x squared, and you can have all kinds of those are quadratic. You can have cubic functions, and these are all in a way they're all in a category called polynomials. But more specifically, those are lines, those are parabolas, these are polynomials. I can go to x to the 4th, x to the 5th. You can have, we are talking about functions, so I'm not really talking about, so I'm not going to talk about circles, and I'm not going to talk about sideways parabolas. Why not?
They're not functions.
They're not functions, right? They fail the vertical line test. A function has to have, for every one input, there's only one output. Look at this guy. If you have one input, he has 2 y values. See them? So it's not a function. It's a thing. It's a relationship. It's a conic section, but it's not a function. By the way, you know what it is? It's x equals y squared. Okay, now listen, it's not a function. I'm trying to talk about functions. But if you solve for y, you can kind of get 2 functions out of it. What do you get if you solve for y? I'm sorry I flip-flop here, but
Square root of x.
yes, and it's plus and minus the square root of x. And I don't know if you realize this or not, but f of x equals the square root of x is this function, which really is the top half of this sideways parabola. Maybe you thought it was his own function, but he's really the top half of this sideways parabola. And if you stuck a negative sign in front of him, he's the bottom half of this sideways parabola. He's the, right? Which is together, you throw it together and it's this, and it's technically not a function. Separated, they're both functions. Separately, they're both functions. Same with this circle. This circle is x squared plus y squared equals 1. A circle is not a function. We're really not going to study circles, really. But if you solved for y, you could get yourself a, what would you get? Solve for y. Solve for y. Move the x squared over. Take the square root. Plus or minus. Now, again, sorry. This was a circle. I guess this was centered at the origin and it had a radius of 1. I wasn't too clear there. So then I wrote this equation, which is a circle centered at the origin, radius 1. But when I solve for y, I get this, which is a circle centered at the origin, radius 1. But you know what it really is? It's the plus and minus. It's the top half of the circle and the bottom half of the circle. So individually, these little dudes are functions. With the plus and minus, I still won't call this a function. But individually, that's a function, and what it is it's the upper semicircle of radius 1. I mean, it's, right, it's this. And with the negative sign in front of it, it's the bottom semicircle. Now listen, I'm talking about all kinds of functions, like there's a million different kinds of functions. To tell you the truth, there's not too many more. There's this clump of things called polynomials. Well, sorry, he's not really a polynomial. So there's these square roots and cube roots, and then there's other functions that aren't really called polynomials. These are polynomials. There's these root functions. What else is there? There's these rational functions. Do you know what I mean by that? What does the word rational make you think of in mathematics?
Fraction.
Yeah, ratio or fraction. And so a rational function is typically, you know, one of these things, 4 minus x over x plus 7. Do you know about those? Can you tell me one thing annoying about those? Yeah, they got some undefined places. You're right. So far, these polynomials don't have any undefined problems at all. I think the domain for most of these functions is all real numbers. But this guy has a domain issue. He's undefined when the denominator is 0. He's undefined at -7. How does that play out in the graph? Actually, it could be a hole. We'll discuss holes a little later. But it's an asymptote. It's a vertical asymptote.
Yeah.
So these rational functions are kind of a pain. I don't know. They're not my favorite function. They tend to look like this. They have these. This guy has an asymptote at -7. He also has a horizontal asymptote at -1. I really don't want to review all those rules, but I'm reminding you slowly of those rules. And anyway, and then they tend to look like him. They tend to kind of look like this. They kind of get guided toward these asymptotes like this. Kind of a pain, right? I much prefer polynomials. But in a way, I'm almost done with functions. I mean, I got polynomial. These are all these algebraic kind of functions. So there's some other functions that aren't algebraic. And by the way, when they're not algebraic, I think that's where this word transcendental comes in. And I don't know if you've noticed, but this book is called Calculus with Early Transcendental Functions. And that means that they very early introduced these other functions, which you know about. Listen, they are e to the x and log x and natural log x. You've heard of those. Yeah, there are calculus books that don't introduce those early because they use calculus to define those functions. And so they come up in chapter 5 or 6. We used to use that book. We've decided, why wait till then? Let's throw in our early transcendental functions. Students, you learn about them in algebra and precalculus. Let's bring them in early in calculus. So now I'm saying that's what that title of your book means. So the e to the x function, he's beautiful. You know what he looks like, right? Maybe. His inverse is the natural log function. It looks like this. These are both using the base e. There's other logarithms that don't use base e, log base 10, log base 12, log base 4. They're all kind of look like this. This is log base e. He's famous. He's known as the natural logarithm. What am I doing? What am I doing? I'm talking about functions, and I'm kind of trying to categorize them for you. And I'm saying we went through a kind of a list of algebraic functions, and now I'm getting into some transcendental functions. But listen, there's only these two. Now here comes some more. Trigonometry. But don't freak out. I mean, there are 6 trig functions. 6. That's it. There's not 12,000. There's 6 trig functions, right? Sine and cosine, tangent and cotangent, secant and cosecant of x. You maybe know about those kind of. The sine and cosine ones are these beautiful waves, you know. We took a look at that the other day. The tangents and cotangents and the secants and the cosecants, they're periodic functions. They have these asymptotes. They're full of these undefined places. Sine and cosine aren't undefined. They have these beautiful waves, right? But the other 4, full of these asymptotes, are kind of a pain. But they're useful. So what did I say? 6 trig functions. Okay, now, by the way, I slowly brought up the word inverse here a second ago. This e function and this log function are inverses of each other. That means they undo each other. That means if you have e to the natural log of x, they cancel each other out. You really just have x. Kind of like, here's a couple inverses. If you have the cube root function of x and then you cube it, those are inverses of each other. What do you really have there? An x. Inverses of each other, kind of cancel each other out, undo each other. So now I brought up these 6 trig functions, so guess what? Each of these 6 trig functions has an inverse. So now there's 6 inverse trig functions. 6 inverse trig functions. Those are really weird. Not really that weird. Hey, but we're done. We're at the end of the list. I mean, maybe you thought there was thousands and hundreds of functions. Well, there sort of are. But, you know, if I'm categorizing them, this is it. We're done. Well, I'm sorry. Yeah. Until you get way up someplace, then you start, high-level engineering, and you can. There's some other interesting functions, Bessel functions and Dirac functions, and anyway. Step functions. See, that's another thing. I don't really. There's step functions. You know, you might have seen those. They're full of these holes and discontinuities. So cool. Algebraic functions, e's and logs, trig and trig inverse. That's kind of our world. That's it. The book sort of talks about all that, although I probably did a better job. This is funny. You know, you can take functions and add them together. You can take functions and multiply them together. When you add them or multiply them, you create new functions. One interesting thing you can do with functions is compose them. You can compose a function. 2 functions. You can do f circle g of x. If I wanted to add 2 functions, I'd have an addition symbol here. I'd be adding 2 functions. But anyway, this little circle means compose or composition of 2 functions. Let me say that. Composition of 2 functions. Hey, here's what it means. It means take the g function and stick him inside of the f function. And I'm going to write it like this. F of g of x. You know, I think of these functions as having an input. You know, the x is the input variable to the function f. Well, in this example, what's the input to the function f?
G.
The g function. The whole entire g function becomes the input to the f function. And so if you if I change this and call this g, and I looked at these two functions, can you do g composed with f? So what am I doing now? I'm sticking f inside of g. I'm sticking f inside of g, so I'm sticking this f function into there, in there for the x, and I create a new function called x plus 2 squared, quantity squared, right. The composition of g and f. It's just another function. In the end, it's just another function, but it sort of came from the composition of these two functions. On one of your on my review that I asked you to do, there's sort of a backwards version of this question. I don't know if you looked at it yet. The homework in 1.3 kind of has a backwards version of this question. Let me show you what I mean by that. Oh, by the way, this is sort of a composition. This is sticking the log function into the e function. And because they were inverses, what happened? They canceled each other out. Right. This is sort of a composition. This is sticking the cube root function into the cube function. And they canceled each other out. Here. So if I give you this function, oh, and there was a misprint on my little review sheet. What problem was that?
5.
On problem 5, how does it read? Find.
2 functions.
Okay, hang on. So it says find 2 functions,
I think you wanted to put f of x.
and I should write f of x. This was missing. So this kind of needs to be inserted in here. Find 2 functions, f of x and g of x, such that, or what did I say?
So h of x
So that,
equals
So-
f of g of x.
so h of x equals f of g of x. See, that's the composition. So h is the composition of f and g. And then I give you h. Now listen, I'm not going to do your problem. I'm just going to do my own problem. So if I make up my own problem, this will look a little different here. H of x is, I'm going to make up this problem, 6 sine of 5x plus 2. So now what's going on? What does this question want? This question wants 2 functions, f and g. And when I wrote it and typed it, I screwed that up. I left out the f of x. So it'll make the sentence will make more sense if you put that in there. So find 2 functions, f and g, so that h is the composition of f and g. And then I give you h. So now your job is to figure out who's stuck inside of who to come up with this. I mean, by the way, in this description here, who is the inside function? G. Thank you. G is the inside function, and it's inside of f. So maybe, can we identify who might be considered an inside function here? Who would you call the inside function? If you were
5x plus
if you were sort of decomposing this,
5x plus 2.
you want to call that the inside function. I do. I agree. That would be 5x plus 2. And what's it inside of? It's inside of the function f, and what should we call f?
6 sine of x.
6 sine of x. I agree. Because then if you stuck g inside of f, you take the entire g function and stick it in here, and would you have h?
Yes.
Yes.
Yep.
Not really too hard, but it's a different style question. What was I doing over here? I was asking you to compose 2 functions. This question was sort of asking you to see the composition already done and decompose it. Yeah. And that's all. You're done. I mean, these questions usually aren't that hard, but you kind of got to know what the hell they want. Conceptual, maybe more than there's not 5 pages of work here. It's just understanding what's written and how to answer the question. By the way, when you do a question like this, there usually is more than one answer. I could do this differently. I could decompose this differently. So this is one answer. This is weird. Watch this though. I'm going to call the inside function, watch this, here's another, I'm going to call the inside function the trig function, sine of 5x plus 2. And then what would I call the f function?
6x.
Good, 6x. And so then if you stuck him into him, which means into the x, you would have the answer. So there's more than one way to decompose sometimes. I mean, I think it's obvious. I think the top one is kind of the obvious one. I got to get kind of creative to come up with this one. I think I totally skipped 1.4, didn't I? I had a little homework list. Yeah, I don't even, yeah, 1.4 was sort of data, modeling data. We tend to skip that. And I am going to skip it, except I want to say one thing. You know, we talk about these functions, we talk about functions in math classes. We've done it for years now. Somebody gives you a function, it's a line, it's a parabola, whatever it is. You know, behind the scenes, what's really going on in real life, people are gathering data. And if you're gathering data and plotting data and it looks like this, perhaps that's, with some errors in there, perhaps that's a linear model. You know, perhaps you could find the line of best fit or the linear regression. And then you never really get to do that in math classes. You always skip over the data part because it's a little bit of a pain. And in math classes, we just talk about the function like it's already built. And it is. And how do you work with functions and what do they mean? But in life, functions come from data. People gather data, they see the pattern, and they either call it a linear set of data, or watch this. If I'm gathering data that looks like this, maybe I can find a parabola that fits that. It doesn't fit it exactly, but there's a scientific way to get the exact or the best fit parabola. If I'm gathering data that looks like this, if I'm gathering data that sort of fluctuates, I would use trigonometry to model that data. Anyway, we always skip that. I'm skipping it myself, except for that 3-minute discussion there. It's interesting. But we're in a math class. I guess we're not in real life. Well, if I head on into 1.5, we do hit this topic of inverse functions. And I know that this can be kind of a weak area for students. I've already sort of touched on inverse functions just on a very basic level. You know, here another basic level. If you've got a function that multiplies by 5, like I guess 5x, you know, a function that, what would be his inverse? He would be a function that divides by 5. If you have a function that squares things, what would be his inverse? Square rooting. If you have a function that adds 2, the inverse would be a function that subtracts 2. So on a real gut level, that's what inverse functions do. They undo what the original function did. Then they show up as what they show up is when you have a function that's when you have an exponential function that exponentiates things, his inverse is a log function, a logarithm.
Is it natural log?
Well, when the base is e, then yes. If you have a function this is an exponential function, this is an exponential function with a base of 2. His inverse would be a log base 2 of x. By the way, the notation for his inverse might be just another function called g, but we use this notation when we know it's his inverse. We call it f with a little -1 of x. That's the notation for an inverse function. Hello. You might be early. That's okay. And that little -1, it's funny, you put it up there, it's the notation for inverse functions. Listen, you put it up there and it looks like a dang exponent, and it's not. It is not an exponent. It's not an exponent. It's not an it's just it's a little notation that means inverse function. It should be clear from the context of what we're doing. It should be clear. But it's not an exponent. You know, hang on. Let's talk about exponent. If you have x to the -1, you know what that means? 1 over x. If you have 3 to the -1, that's 1/3. But this is not 1 over f of x. It's not. It's a notation that means he's the inverse function of this. It's not an exponent. Not an exponent. So exponential functions have inverses that are logs. And I call this an exponential function, and this is his inverse. But then we use the phrase the exponential function. The exponential function is base e, e to the x. By the way, e is 2.7. It's just a number. 2.7, blah, 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 blah. It's an irrational number. But when we use that, it's a famous base to use for exponential functions, and we call him the exponential function. And his inverse is a logarithm base e. I could write log base e, but guess what? Nobody ever writes that. When it is log base e, we write the natural log. Right. And the base is understood. The base is understood, which is what?
I was saying it's basically the same thing as like with regards to e, right? Like you can call it log e or natural log.
Okay, right. These are the same.
Yeah.
Yeah, those are the same.
Okay.
Hey, these are not the same, right? They're inverses of each other. They're closely related functions. They're cousins of each other.
Yeah.
He's one, and he's the inverse of him. Right. Right.
I'm saying like.
Yeah, those are the same.
Yeah.
Yep.
I used to get those mixed up.
Yeah, well,
but now you explain it.
Yeah. Look at this. I'm going to keep talking here a second. I'm going to get rid of this one. You know, let's do something here. Watch this. Let's plot a couple points here. Please plug in a 0, please.
1.
Good. 2 to the 0. Anything to the 0 is a 1. Plug in a 1. Plug in a 3. 2 cubed is 8. Okay. So, you know, I have my inputs and my outputs, right? I have this set of numbers. The whole set of these numbers is the domain. The whole set of these numbers is the range. But individual members are inputs and outputs, or x's and y's. Okay. All right. This guy. If I've made a chart for him, plug in a plug in a 2. And if you plug in a 2, I don't know.
Why would
Yeah, logarithms are a little funny. Some people still don't have a hold on a grasp of what the hell is a logarithm. Here's what the hell is a logarithm. It's the exponent. The answer to a logarithm is the exponent you put on that base in order to get that number.
right?
So if I plug in a 2, then I'm looking for the exponent you put on 2 in order to get 2. What exponent do you put on 2 in order to get 2?
1.
Thank you. So if I plug in a 2, the answer is 1. If I plug in an 8, then I'm looking for the exponent you put on 2 in order to get 8. 3. I could go on and on, but I don't really want to. My point is, notice something. If this is a function and this is his inverse, the x's and y's of the function are switched. The y's become the x's become the y's. That's true. The inputs and outputs are switched. The domain of him is the range of him. The domain of him is the range of him. The domains and ranges are switched. What I'm really trying to get to for these inverse functions is that is back to this trig. So when it comes to trigonometry, what you do with trigonometry, I think you guys know, is you plug in angles and the answer spits out numbers. And when you plug in those angles, they could be in two forms. They could be in radians or degrees. It doesn't matter. When you plug in the angle, it could be radians, it could be degrees. They'll both spit out the same number. In other words, I can do the sine of 30 degrees. Anybody know the answer? 1/2. You're supposed to kind of know that stuff, but if you are allowed to have a calculator in this class, and you're allowed to punch it in real quick, but you probably aren't quicker than me if I haven't memorized. But what if I'm in radians? Instead of 30 degrees, I might say pi over 6. But guess what? The answer is still 1/2. But again, what am I doing with this trig function? I'm plugging in angles, and it's spitting out numbers. Is kind of the way I like to think about it. I don't know. I like to think about it like that because then when it comes to the inverse of him is this. Sine inverse of x. Although, to avoid the confusion of whether that's an exponent or not, but we all know it's not, right? But to avoid the confusion of whether that's an exponent or not, there's another notation for sine inverse. It's called arcsine of x. It's the same thing. It's the same thing. But this is the inverse function of him, and so now I want to say that the input is a number, and the answer, the output, is the, what do I want to say? Is the angle. Yeah, and that angle could be in degrees or radians. You know, that degrees or radians is sort of like just a unit. I mean, if I measure this table, I can measure it in feet or I can measure it in inches. It's kind of just a unit. It's not some freaky thing, really. I can measure angles in degrees or I can measure them in radians. How many degrees does it take to go all the way around this circle? 360. Those are little teeny things called degrees. How many radians does it take to go all the way around this circle?
2 pi.
2 pi. And if you thought of pi as a number, that's roughly 6. 6.28. So radians are bigger. 6 of them around this circle. Degrees are teeny. 360 around the circle. But they're just like inches and feet, kind of. It's just a unit of measurement for angles. What's cool about radians, though, see how I'm saying you input angles and you spit out numbers, and then you you input numbers and you spit out angles. I mean, that's just the concept of what the trig and the inverse trig function are doing. Let's do an example. So if I do, what's the sine inverse of 1/2? Well, you just did it. The answer is
30 degrees.
30 degrees. Again, depends on the problem. When we're doing a lot of this calculus, we do want to, I guess we should use radians, I think, as answers, for the most part. I think we're all more comfortable in degrees, so I tend to talk in degrees just to ease your pain, but we should be able to do both. We should be able to do both, so maybe I should cross that out and put pi over 6. I mean, it's not wrong, but it's... Hey,